Well, welcome everybody. Thanks so much for coming out tonight. My name is Shay Ramquist, and I am the director of TrinityU, and I'd like to welcome you to the fourth and final TrinityU lecture of our 2018-2019 lecture series. Tonight, we have a treat. We will have Sarah Carty talking to us about math in the enchanted universe. Sarah has been with us here at Trinity for at least 5 years, and she's been in education for much longer than that. She's an excellent teacher in our math department, so excellent that she has been recently made the chair of the math department. And we've been thinking for a few years now about how can we make our math program more classical, not just turning our students into faster human calculators, not just trying to increase their SAT scores or get them ready for STEM fields. No problem with those things. Those things are all helpful, but maybe there's a deeper purpose for math. And so we want to explore that with you tonight, or Sarah's going to explore it with us. So let me pray for us to begin us, and then I'll pass things over to Sarah. Heavenly Father, you have created the universe with its endless galaxies and brilliant stars and planets, and this favored planet upon which you've placed human beings. We ask that as you have created all things and created our minds, that you would enlighten us tonight, open our minds to your truths, speak through Sarah, allow us to know you better and the world that you've created better through what we hear tonight. We ask these things in the name of Jesus, our Savior. Amen.
Good evening. A little bit of housekeeping. Oh, gosh, thank you. A little bit of housekeeping. There was several items to pick up on the way in, so please make sure you've got a handout and some scratch paper. More than one piece is what you'll need. There's rulers, you'll need a compass, and there's little golf pencils if you don't have something to write with. And also there's a couple of dry erase boards if you need something to write on. So yeah, there we go. Fabulous. This is going to be an interactive evening. So you'll get out what you put in, as I say to my students. All right. So mathematics and the enchanted universe. It's kind of a big title. So let's first talk about our students. We all have that in common here. Our students, they learn to add, they learn to subtract, then they multiply, then they divide. And they deal with the natural counting numbers. And then they move to fractions and to decimals and percents. All of this in preparation for algebra, geometry, pre-calculus, beyond. So when you're looking at the whole math education, you see a shift. You see a shift from concrete ideas like counting numbers on your fingers or crayons in a box to more complex and abstract ideas like unknown variables, x, or perfect shapes, perfect circles, or the number infinity, very complex and abstract ideas. And so a child's thought that matures from thinking about the concrete ideas to abstract parallels the evolution of mathematics. So the oldest form of mathematics is geometry. This is lady geometry. This is my favorite painting from a professional perspective. There's so many things in this painting, I could talk about it for a long time. So we're going to focus our talk this evening on geometry because it is the oldest math. And it started out, not a very good driver yet, the ancient Babylonians and the ancient Egyptians. And so the ancients there, they used math for, they needed technology in creating their religious structures. They created no theories or bodies of knowledge. And they were interested mostly in the heavens for religious reasons, and also the calendars for their farming and their growing of crops, and when floods would come and when it would be a dry season. So then along comes the ancient Greeks. And this is a very famous painting of the University of Athens. And it has kind of all of ancient Greece's who's who in mathematics. And right in the middle are Socrates and Aristotle. But there are also other famous figures. You have to look really close and kind of know your Greek history to look and know who these people are. So right on the corner, there's Euclid himself. So look at what you can see. It's Euclid. He's got a compass, and he's telling somebody how to construct something. And so the Greeks, they harnessed the power of human reason, and they created new branches of culture with it, like politics and philosophy and architecture. And then they more specifically systematized mathematics. So Socrates and Aristotle, they considered idealized versions of form, and I'm going to kind of refer to them as abstractions. And the study of these forms then led them to thoughts of imperishable and eternal things, the idea of the good. And so our 8th graders have these conversations a lot right now, particularly with their 8th grade orals coming up. Math bridges from the concrete to the abstract very uniquely. So we can see and manipulate geometric forms and then go about and proving truths about them in a more abstract manner. So they used reason to deduce new truths, and they called that the Axiomatic Method, which is a fancy way of saying deductive reasoning. And this all came from the ancient Greeks. Euclid, our buddy Euclid, compiled all of these ideas into his book known as The Elements. And we will get into looking at the elements, and it's one of the propositions tonight. But the Greeks themselves recognized this broader significance of Euclidean geometry, and Aristotle stressed that the Euclidean procedure must be the aim and goal of all sciences. Each science must start with fundamental principles relevant to its field and proceed by deductive demonstrations of new truths. This idea was taken over by theologians and philosophers, political theorists, and physical scientists. So whatever happened? Well, along comes the Romans, and they take over the ancient Greeks, and their purpose with mathematics was not to pursue new knowledge or to continue on for the sake of knowing. They used it to aid in engineering, and they are very good at engineering roads, at engineering aqueducts, engineering bridges. And so this also led to the spread of the gospel, right? So the Christians came along and gained power in the Roman Empire, and they destroyed anything that came from these ancients, the sources of learning. So sources of learning were, much of that was lost. Much of the knowledge was lost during that time period. However, also during that time period, the Arab Empire grew, and they appreciated a lot of the ancient Greek work to the point of translating a lot of the ancient Greek texts. However, they did not further the knowledge or the pursuit of knowledge either. They were more librarians. They kept it and took care of it, and it's thought that there's probably a lot of literature still out there that we haven't discovered in Arabia, in that region. So then, how on earth did we in the West come to know about Euclid if it just stuck around in the Middle East? Well, during the Crusades, there was contact from the West to the East and back again, and also Arab trade brought the contact with Europe. And so with those ideas, the texts came back to Europe. And there was also a thought they were translating from Arab and Greek now into Latin. And so now we've got Euclid's Elements. So this is the Renaissance period, by the way. And during the Renaissance period, Plato and Aristotle and Socrates, they all were kind of new, the old is new. Old school is now new school. And so their thoughts of forms were used, and they were used by artists now in painting and in sculpture. They were thinking about the ideal human body, the ratios within the ideal human body. And perspective art started. So things like Da Vinci's Last Supper, you can see where there's the background. It was painted on a wall, and so it looks like the wall that there's a corridor behind the table in the Last Supper because of perspective. And there's also a rediscovery and translation of the elements now, and it's into Latin. This one happens to be into English, but it was now translated into a Western language, or back into a Western language. And the elements are made up of two types of proofs. There is construction, and there are theorems. So the constructions are the creative part. They are the creativity is a major component to mature abstract thought. And so creating something from nothing is like doing the work of a creator. And so geometry challenges our creativity. So this is where you're going to start your part of tonight. We're going to construct. Now you have the technology of the time in your hands. You have the straight edge and the compass. We're not going to call it a ruler. Got it? It's not called a ruler. It's called a straight edge for a reason. And a compass. Now, there are a couple of rules you have to follow and rules that you can't follow. First, a point must either be given to you or be the intersection of things that have already been constructed. Your straight edge can draw a line through any 2 points, and your compass can draw a circle through any given point with any given radius. Now, the things you can't do. You cannot use the tick marks on the straight edge to measure. Those are concrete. We have now entered into the world of abstract. You will not be precise if you use those tick marks, because they're not exact in our world here, okay? And it will be assumed that as soon as you lift your compass off of the paper, it'll just flop shut, so you can't use it to measure lines. Got it? Okay, you've got your rules. So, here are the moves you can make. You can draw a straight line from any point to any other point on the page. You're allowed to do that. You're allowed to extend a straight line as far as you want, and you can draw a circle with a given radius. Those are the only 3 things you're allowed to do. Let's make a few creations. So let's start with the first one, given 2 points. So if it says given, that means that it exists there. So you need to put on your paper 2 points. 2 points, anywhere on the paper you want. A point is not a big circle, it's just a little dot. It's just supposed to represent a location. It is that without breadth or depth. And then you're going to take your compass. There you've got the point. If you've got, most of you probably have the compass that opens up like this. Put the pointy end on one point and the pencil end on another point, and you can work on drawing your circle. If you have a different type of compass, I actually like the other type better. I think it's a little more user-friendly. You put the middle of the flat circle on one of your points, and then you put your pencil on the outside, and you do this with it. Yes, Dr. Bueller. Totally. Because really, your paper is something finite, and we're working in this world of infinite perfection. All right, given a line, so you need to draw yourself a line on the paper. I would say just because you have a finite piece of paper, maybe make your line about 2 inches-ish, about that distance, just so that things don't wind up going off of the paper. So draw yourself a line, and now you're going to take your tools, and you're going to construct a line that is twice as long as what you just drew. You have to think creatively about this. Do you remember anything about circles? Do you remember anything about circles? Oh, say it the other way around.
Pardon, the diameter is double the radius.
There you go. The diameter is double the radius. So if you have a radius of a circle, can you just extend a line across the circle? Oh, now it's double. It's now the diameter, and it's double this line that you drew originally. A little creativity there. All right, so here's the trick. And this is going to take, there's a few of you who have done this before, so help out, but don't give answers, okay? You are going to construct an equilateral triangle. Well, there's a fancy word. Equilateral. Let's break it apart. What word do you see in the front of equilateral? Equal, okay, we know what that is. Lateral, what do you think? Lateral. If a football player makes a lateral move, what does he do? Side to side. So you're making equal lines, right? So it's a triangle with 3 equal sides. Ready, go. Draw a triangle with 3 equal sides. And they have to be precisely equal, exactly equal. Exactly equal. You already know. You're thinking. Oh, there it is. I see. Yes, good. Do you remember how to do it, Shane? Good job. Oh, you approximated. We're in the perfect world. Shane will help you. He's good at this. How are we doing? How are they doing over here? How did you do? I don't know. You might need a circle to help you. That's just a hint. Don't tell anybody else. Oh, it looks like an approximation. How do you know it's equilateral?
2 inches.
Oh, but we can't use the tick marks on our ruler.
Oh, we can't?
No, that's a rule. Oh, that's a beautiful circle.
Oh, can we use the compass?
That might be helpful. She did a good job. Mr. Carty, how are you doing?
I'm not very good at operating this compass. Is there a qualification I should have gotten before I showed up?
This one's a lot better. This one's really great.
Oh, I kind of want to master it, but I also want to actually.
Very good, Mr. Alderson. Proud of you. How are you? Oh, I like it. There you go. So for some of you, it comes a little quicker. Others are still thinking about it. That's what's kind of fun about it, though, too, is you don't have to be a rocket scientist to do this. I was poking my husband a little bit. All right, so how did you do? Got some circles? Remind me, I put this in my pocket over here. All right, so you've got a circle, all right, with a radius. And then you can draw another circle with the same radius. This is where my drawings get a little weird. All right, and they meet right there, yes? And now we can start connecting lines. Remember, you can always draw a line between 2 points. There we go. We've constructed our equilateral triangle. Some of you got it, yes? Some of you didn't do complete circles, totally fine, didn't have to. But we're going to need those circles later on. So this is the creative part of geometry. There's also the other part that we talked about. Actually, you know what? Let's do this next. That's a better idea. We're going to do what's called a particular construction. So if you haven't written on the back side of your paper yet, flip over your scratch paper. We're going to kind of do a clean page, blank page. And you need to draw yourself a line, and like about 2 inches-ish. Eyeball that. It doesn't have to be precisely 2, but right around that line or that size, that'll help us with our construction. And we're going to now label parts so that we can all be talking about the same thing. So we're going to label parts on our line. One side A, the other side B. And we're going to let that be the radius of a circle. So now go ahead and draw an equilateral triangle using this as your radius. So you'll do one circle and the other circle. All right, go ahead and do that. It'll look perfect now because you've had practice. Wow, that looks bad. And that intersection point, we're going to label C. How did you do this time? Easier? Now it's like you can't unsee it. You know, you can see it every time. You know how to do it every single time. All right, so you drew this is our particular construction. We're going to come back to this guy. All right, so just hang on for just a minute. And we're going to follow the axiomatic method. Now, these are two famous Americans up here. Do you recognize? The one's very recognizable. How about the other one? Jefferson. Well done. So Thomas Jefferson, what did he do? What's that? What didn't he do? That's a good question, actually. He was a bit of a Renaissance man. He revered Euclid and the elements. He loved Euclid. In fact, when he retired, he stopped reading newspapers altogether and started to study the elements and other mathematics in his retirement for relaxation. So Thomas Jefferson, actually, he used the axiomatic method when he penned the Declaration of Independence. So proofs are really just baked in to our government document there, right? He used the axiomatic method so that when he wrote the Declaration of Independence, by the end of it, it was just evident that the states should govern themselves. Lincoln, again, also revered the axiomatic method, and Euclid, he studied Euclid's elements all on his own, late at night, by candle. So many things that are very confusing about that. But he studied that, and he loved it so much, and he used it to argue as a lawyer and as a statesman, particularly for the abolition of slavery. So Euclid's elements has been a part of our American history for a long time. In fact, have you seen the movie Lincoln? There is a portion about an hour and change in where Lincoln is talking to Kylo Ren, who it's Adam Driver, the actor, but you can't not think of him as Kylo Ren. And he's talking about Euclid's elements. And if you look at your handout that I gave you, it has the postulate. Is it postulate number 1? What does postulate 1 say? Things which are equal to the same thing are also equal to one another. So he quotes this in the movie Lincoln as he's talking about slave men and free men. And he uses Euclid's elements as his inspiration in the movie. Urban legend maybe, but I think it's pretty neat that Lincoln was known enough for that it would be inserted into a major motion picture. So looking at Euclid, I would really like you to focus in on a few of these definitions. So you're all looking at your Euclid's elements, book 1 there. And you've got definitions. It's broken into several sections: definitions, postulates, and common notions. So definitions are what mathematicians love, because we can all be talking about the same thing. When I'm talking about a circle, Shane knows exactly what I mean by a circle. When I'm talking about a line, Miss Kim knows exactly what I mean when I'm talking about a line. He defines his terms so that further on in the book, everybody knows what he's talking about and knows what he doesn't mean. So there's the definitions. I want you to particularly focus on number, actually it should be 15. Look at 15. We've been drawing a lot of things. 15 is a definition about what? A circle. All right, what do we know about a circle, or how does he define a circle? It's a plane figure, not flying figure, but it is on a flat surface. It's on a plane, so it's a plane figure contained by one line, such that all the straight lines falling upon it from one point among those lying within the figure are equal to one another. What are those lines that they're referring to? The radii, yes, the radii of the circle. So all radii are equal. That's what he's saying in here. Okay, so there's definition 15. Take a look at axiom or common notion. Axiom is a synonym for common notion. Those things are talking about equality. So things which are equal to the same thing are also equal to another. Equals be added to equals. The wholes are equal. Same thing with subtraction, and so on and so forth. Then you've got postulates. And postulates are kind of, I guess you'd say they're the rules of construction. So draw a straight line from any point to any point. Produce a finite straight line continuously in a straight line. Describe a circle. Describe, by the way, means draw. Describe a circle with any center and distance. All right angles are equal to one another. So that's the breakdown of the very beginning of the elements. He hasn't even started proving anything yet. He's really just defining his terms. Okay. There are also, through the entire book, there are these propositions. So I wrote down for you proposition 1. A given finite straight line to construct an equilateral triangle. That's what he's going to do, what he's going to prove to you. And so the elements actually is made up of 13 books. And so there's over 400 propositions that are proved through these 13 books. We're looking at one tonight, okay? And so we're going to prove proposition 1. All right, here we go. Is that it? Oh, I don't want spoiler. Nope, don't look. Okay. So let's go ahead and look at our definition 15, not 11, axiom 1, postulate 1, and 3. Think about our construction. What was the very first thing we did in our construction? What was the first thing we did in our construction of the equilateral triangle? We had 2 points and did what? Made the line, right? Y'all did that? Okay, so we had a line. We were given line AB. Now, what says that we can have 2 points and a line through it? Take a look at your Euclid elements. Is it a definition? Is it a postulate? Is it a common notion? What allows us to say that? Definition 3, the extremities of a line are points. Check the postulates. Draw a straight line from any point to any other point. So postulate 1 says, yep, it's legit, you can do that. You can do that. Okay, what was the next thing we did after we drew the line? Now what do we do? You drew a circle. Okay, so now take a look. What does it say? What allows us to draw a circle? Postulate 3. Describe a circle with any center and distance. All right, so we draw circle. I'm going to call it circle A so we know it's the left circle. Postulate 3. What was the next thing we did? Drew the other circle. What should we call that circle? Draw a circle what? B. All right, postulate 3 again. See, we have to explain every single step we make here. It's kind of annoying, but it's beautiful once you're done. All right, now what did we do? We have our 2 circles. Now what? We marked the point. All right. And then we drew the radii, so we drew a line from A to C. And what allows us to draw a line from A to C? What allows us to draw AC? Don't think too hard about this, by the way. Postulate 1 allows us to do this, yes. What is the next thing we did? There you go, write it down. Draw a line BC. Postulate 1. Okay, but what are we trying to show that this guy is? The whole purpose is to show that this is equilateral. And what do we know equilateral to be? All 3 sides have to be equal. Have we talked about anything about lines being equal yet? No, so should we start down that path? Probably. Okay, so what's equal to what? AC, okay, AC is equal to AB. Why? They're radii of the same circle. So let's take a look at our definitions. What tells us that? Definition 15, yeah. All right. So we have 2 of them that are equal. Do we know anything else to be equal? Do we know any other things? So remember what keep in mind our goal. Our goal is equilateral triangle, all sides being the same. We showed that this is equal to this. What's next? AB and AC are equal. AB equals AC by definition 15 again. Oh, thank you. BC. AC. I don't want AC. AB and BC. Thank you. I'm getting excited. Okay. So here we go. Are we almost there? Almost. We're getting closer. We're like a step and a half away. What else do we have to say? Think about what we're trying to show. All three are equal. AC and BC have to be equal. Are they? AC equals BC. Why? Axiom 1! Yes, that's what brings us home, friends. So by Axiom 1. Axiom 1. Axiom 1 says things that are equal to the same thing are equals. Right. So there's Axiom 1. So there you go. Triangle ABC is equilateral on finite line AB. So take a look at Proposition 1 again. A given finite straight line to construct an equilateral triangle. Did we do that? We were given a finite straight line AB. We constructed an equilateral triangle, and we showed that it is, in fact, equilateral. Now, our students, they go through, and they now have to write this in a paragraph. For time reasons, I will not have y'all do that, but it should read something nice, like this. It is required to construct an equilateral triangle on the straight line AB with center A and distance AB. Let the circle BCD be described. So on and on. So you have to say every step in a sentence along with your reasoning why. Putting it into a paragraph really solidifies that your understanding in your mind. Now, my paragraph might look a little different from your paragraph or the person next to you's paragraph, because we just use our words differently. However, we're all getting to the same location, and we're using the same reasoning. All right. So the axiomatic method. There you have it. Congratulations, by the way, if you've never done that. Well done. That's a huge accomplishment. You can go home. If you have a 10th grader or older, you can tell them that you did a proof tonight. It's pretty impressive. Okay. So how does this help our students? Well, to pass from knowledge of the world of matter to the world of ideas, man must train his mind to grasp ideas. The study of mathematics helps make the transition from darkness to light. Mathematics is, in fact, ideally suited to prepare the mind for higher forms of thought because, on the one hand, it pertains to the world of visible things, and on the other hand, it deals with abstract concepts. It's very uniquely suited for this. Using the past to inform the present. Let's look back really quick. Humans study nature. They study it to know it better. They study it to use it to improve their life, to make predictions, and to eliminate the fear of nature. And through mathematics, the secrets of nature are revealed. So we're definitely part of a STEM-focused culture: science, technology, engineering, and math. It's a really hot-button word. It's used a lot. You probably get a lot of emails about STEM camps and STEM classes all the time. However, and our children will enter a world full of technologies and problems to solve that we haven't even dreamt of. So it's important that our children achieve mental maturity and be agile thinkers. So remember the course of mathematics history we talked about. The Egyptians and Babylonians, they reflected their ideas of religion in their structures and used precise, albeit time and resource-consuming methods. They used slave labor, and they had a lot of time to do this. The Romans harnessed math's precision and calculation with incredible engineering feats. So now water is getting into cities, and there's sewage systems, and there are bridges and roads to spread the gospel. The Greeks sought knowledge beyond utility, and they asked questions about truth and beauty. The axiomatic approach, it established the standards of rigorous arguments to draw conclusions and increase knowledge. So mathematics is not number crunching or algorithmic processes. Rather, it's a discovery and recognition of creative relationships at levels of abstraction all across all fields of knowledge. So as seen through history, once man seeks to answer questions about nature, it's a natural next step to ask questions about one's purpose in nature. Why are we here? What purposes should I serve? What is truth, and how do I find it? So when we look back on the history of math, and particularly geometry, we see the evolution of these questions over time. The Babylonians and the Egyptians reflected their idea of religion. The Romans harnessed it and used it to serve their purposes. The Greeks extended it and looked at abstracts, truth, and beauty. So educators must be honest and ask themselves, what questions are they training students to answer? Do we wish our children to be number crunchers and algorithm processors, or creative, agile thinkers? Thank you.